All right, I'm recording now. Um, this is the this is just the space. This is just kind of showing you a transverse view. Like here's the lungs on both sides. So that's probably looking from above, like down into the heart. Um, and then here's like another view of it. I guess that one's even like a little bit better for what I want to kind of show you. So that's called this is like a space that the heart sits in. And I'm sure it's marked somewhere, but I'm going to write it again. But not in that brown color. It's called the mediastinum. That's just the cavity. Right. So the heart's sitting there in a cavity called mediastinum. Let me go to the next slide. Fine, that's probably where I wanted to be. The heart has layers. So if we're actually grabbing the heart and touching the heart, we are touching this layer right here. It's called the epicardium, which I'm looking for. I'm just going to mark it. So if you were to grab a heart, like let's say that those models in lab, right? When you pick it up, you're touching the epicardium. And it's just a very thin layer. It's like the outer layer of the heart. And then there's the actual main part of the heart, like the muscle part of the heart. We call that the myocardium. That's right here. Myo meaning, muscle. So the main meat of the heart is the myocardium. And then the inner lining of the heart. So if you were to like stick your finger inside a ventricle or an atria and like rub the wall of the atrium, you would be touching the endocardium. Myocardium is the word that's used. Endocardium is used because sometimes there's something called like endocarditis where that would become inflamed. But essentially the epicardium is outside of the heart. The heart muscle itself is called the myocardium. For example, like a heart attack is called a myocardial infarction. It's got that word myocardium in it. Endocardium is the inside. You're touching the inside, the like the lining of the atria or the ventricles. So we've got that. That's like the heart, okay? But then we've got something else here. So let me erase this. We've got this part here. So I'm just going to kind of outline a little bit of it. There's like a little outline, right? So there's something else here. That's like the sac that goes around the heart. If you were to open up a cadaver, cut through the sternum, open it up, you're not going to see the actual heart with the blood vessels outside of it and all that. You're going to see a sac around it. You have to cut that sac open, and then what's going to happen is liquid's going to come out. Then you're going to see the heart, right? So the heart is actually surrounded with a sac called the pericardium, right? So there's the pericardium, and then there's fluid inside, and then the heart sits inside of that. So there's the pericardium, there's pericardial fluid, and then the heart. So the heart is kind of in this type of womb with water, and it's got some little bit of a cushion. That fluid can become inflamed too. You can get something called pericarditis. Right? So endocarditis, pericarditis, those are two things that sometimes can happen to people. But That's what this is showing. This is the pericardium right here. And there's different layers to it. Essentially, just remember this. There's two layers. One layer is called visceral. And then one layer is called parietal. It's not just with the heart. When you see these two words, visceral means closer to the organ, and parietal means further away from the organ. So right here, I'm just gonna like outline it in red. I've got these two layers. Between those two red lines, I've got one of those red lines is closer to the heart, so we know that that's going to be the visceral layer. And then one of those layers is further away from the heart, that's the parietal layer. It's like if we're talking about New Orleans, you have the East Bank and the West Bank. The East Bank is going to be the visceral layer because that's the closest to the city. And then the West Bank of the Mississippi is going to be the parietal layer, right? And then the Mississippi River is the parietal fluid. Good morning. How are you?
Had the rough start this morning.
Had I stayed in my office, for some reason I can't share my screen. So if I stayed in my office, I would have been messed up anyway. So it's going to be like that with the lungs, kidneys, lots of different organs. There's a visceral and parietal layer, but we'll get to all that later. So for now, you have a pericardium that surrounds the heart. I won't really ask you these terms necessarily on a test, but they're terms that you should know just for like future stuff. Visceral is always closer to the organ. That's just another view of it. Here we go at the front of the heart. So that's typically what a heart looks like from the outside. So let's look at a couple of things that we probably recognize. Here you have so you've got these 1, 2, 3. We're going to count that as 4. You've got these 4 big vessels on the outside. All right, so you've got and they've kind of color coded them here based on what type of blood they have. You know, things that are red tend to have oxygenated blood, and the blue things tend to have deoxygenated blood. But we've got the vena cava, inferior, superior. So if you look at all the veins in the body, they're all going to converge into one of those 2 vessels. Let's see if I can find you a good picture of it. I don't have one. I mean, with this. You know what? I'm gonna let me just open this up. I got another slide where there's like a frontal section. So, but you can see, before I go into it, you can see some blood vessels on the outside here, like these red ones. There's also these are some arteries. If you see this artery here it's tapping off of this aorta, right? So this is the vena cava, aorta, pulmonary trunk. Those are your big vessels up on top, right? And then these, like this, see that vessel here? It's going like this. If I were to follow it through, it's tapping in right there. And this vessel is coming behind here, and it's tapping into there too. So both of these vessels are tapping into this aorta, and we'll get to that in a second. And then you have the pulmonary trunk. If you see this is going to go, like if you go this way, that's on its way to the lungs. Like the lungs are right here. So this is like a pulmonary artery. And then if you follow it, it's kind of weird. It drops behind both of these. There it is. That's going to the other lung. So those two blue things are pulmonary arteries. They're carrying deoxygenated blood. Like, look at the color of it. It's blue. But we're calling it an artery. Where usually we call arteries like these are arteries, right? This is the artery that's going around your shoulder, and then that artery here is going up your neck, your carotid artery, right? And they're clearly red. These are blue. It's not about the type of blood that's in them. It's about the direction that it's going, right? So these are going away from the heart. This is going to the lungs. And then this is coming back from the lungs right here. These four arrows, right? So there's these two are pulmonary veins. Same thing on this side. Coming in that way, coming in that way. Those are pulmonary veins. But let me erase all that because let me try to show you a different view. That's the back side of the heart. We're not going to really deal with it right now. It's just what you can see is the aorta, how it loops over. It's going to drop down behind the heart and go underneath the heart. But let's look at the let's look at a section of it. I was drawing this last class as a box, but it's not really a box. Let's look at let's outline a couple of our, let's outline the atria first. So let's do the right atria. Can I pause this? Find out. Nope. Here's the right atria, and here's the left atrium. There's the right atrium and the left atrium. And then let's look at the ventricles. They're kind of, it's not like that easy to, this is giving you like a rough idea. There's the right ventricle, and then here's the left ventricle. So they're not like very clear. And you see there's in between, just like in between your nostrils, you have like a septum. In between your ventricles, you have like a septum. So this is all myocardium. This is a muscle, heart muscle. So this is myocardium. So this is the ventricular septum. It's the septum between the two ventricles. So it looks a little complicated if you're looking at it the first time, but essentially what's happening, let's follow some blood through. Let's start here. This is all the blood coming back from all your veins. So all the veins in your arm and your jugular vein in your neck and the veins from your legs, they're all bringing deoxygenated blood back from your body. It's going to come in through here and down there. So for example, the veins in this arm are going to come around my shoulder, subclavian vein, and they're going to go into the superior vena cava. The veins in my legs, they're all going to drain into the inferior vena cava. So either way, they're going to end up in this aorta. So there's the blood. It ends up in that's the aorta, atrium. It ends up in the atrium. So there's the blood in the atrium. The blood's then going to go through that valve. So there's one of your AV valves. There's the tricuspid valve, and the blood's going to go into the right ventricle. So it's coming through here, it's going through the AV valve, going into the right ventricle. This is where it looks kind of weird, because what's happening here is that once it's in the right ventricle, it's going to kind of curve upwards and get ejected out of the ventricle. So it like comes down here and then it goes that way. And it's going to leave. See, there's the door. There's the other valve. This is the valve. This is the tricuspid valve. The blood's going to leave the atrium. This is the pulmonary valve. The blood's going to leave the heart. So it's going to go through here, and then it's going to go out to the lungs. So it's come down here, atrium, ventricle, and then it goes through the semilunar valve, the pulmonary valve, into the pulmonary trunk. These are the pulmonary arteries. They're going to the lungs. So the blood goes to the lungs. It's going to drop off its carbon dioxide. It's going to pick up oxygen. It's dropping off the carbon dioxide. This is the lung here. It's picking up the oxygen. Now it's going back into the heart. So out through the artery, back into the veins. Same thing on this side. It's just harder to see it over here. Out through the artery, back in through the veins. There's another vein right here. So if we were to follow these two veins, they go back here, and then the blood comes out right there. Right, like this arrow is coming behind the heart. We can't see it. And then it goes into here. Same thing here. This pulmonary vein right here, going behind the heart, and then it's entering there. So you got like 4 holes inside this left atrium. A hole for that, 1, 2, 3, 4. So there's 2 veins. And they're red, which throws us off, right? But a vein is going toward the heart. So now it's oxygenated. Now it's on the left side of the heart. So let's follow that through. Down through the mitral valve into the ventricle. So this oxygenated blood goes from the left atrium through the mitral valve into the left ventricle. Now it's going to leave the heart. So it's coming down. Now it's getting pushed out. It's going to go through that aortic valve and out to the aorta. Just so this is in our way, but it's going that way. So it's going out through the aortic valve and then through the aorta. And this aorta is going to go everywhere, right? This right here, subclavian artery, that's subclavian is like your clavicle, your shoulders. So it's going around your shoulders. That one's the carotid. That's going to go up my neck. This is going to split again. Oh, my shoulder. I'm going to try to do it with my right hand. Wait, I got to do this now. There we go. Wait, I'm doing it. I'm like so good at art. Something like that. That's going to split again. That's your carotid on your left side. That's your carotid on your right side. So these two are going up your neck. That's going around the shoulder. That's going around the shoulder, right? So they call this a brachiocephalic trunk, but it's going to split. You just can't see it here. It's going to split and become like, so these are your 2 shoulders, your 2 subclavians. Those are your 2 carotids going up. And then it drops down here underneath the heart. So these are going to your arms. That's going to your head. This drops underneath your heart, and that goes to like everything, right? As it starts going down your abdomen.
Hey, Mr. Falls. Hey, the screen is blank.
The screen's blank.
Yeah.
Is it blank for all of you?
No, I can still see it.
No, I can still see it.
Has it been blank, Kevin, since you started?
No, it was my phone. I had to
Oh,
back off.
okay.
Sorry, I'm sorry.
Are you good? Okay. And then that's it. It goes to everywhere in your body, right? So let's use the head as the example. So this is the carotid, right? This is going up to your head. So that's oxygenated blood up to your head. And here's a jugular vein coming down your neck. So that's oxygenated blood going up to your brain. There's deoxygenated blood coming back down from your brain. And this isn't actually, I don't believe this is the jugular vein. I'm just calling it that. So the artery going out to your head, there's a vein coming down your neck, and that's going into the superior vena cava. So it's kind of circular. There's a lot of crap going on in here, but let's look at some of the things. Let's look at these AV valves first. You've got one AV valve here, and you've got the other AV valve there. So we got two AV valves, atrioventricular valves. So I'm calling them AV valves, although if I wanted to talk about one side versus the other, I would call this tricuspid, and I'd call that bicuspid or mitral valve. So what you can see here, if you look at let's look at this let's look at this tricuspid valve, right? There's these cord things. Right, I'm just kind of drawing all over, but you can see them on the other side. And they're attached. It looks like they're anchored right here, right? It looks like these are pulling the valve open, but that's not at all what's happening. When these valves are open, these cords are really loose. And when this valve's shut again and closed, these cords are really tight. So these cords are preventing, like that valve opens this way, but you don't want it to open, you don't want it to go that way. You want it to open into the ventricle, but not back into the atrium again. So you want it to stop right there. That's what these cords do. They prevent the mitral valve from prolapsing into because you don't want, if the valve's supposed to be straight closed like that, right? But if that valve were to, like, let's say, go like this, then blood's going to leak back. It's going to go back into the atrium again, right? And that just means if you've got blood going in here, it's not going to leave the heart. You want the blood to leave the heart. You want these doors, you want this valve to shut, pretty straight. And that's what these cords do. They're called, and that's more of a lab thing. I mean, it really is. For lecture, I'm interested in how things work. In lab, I'm more interested in, like, what are the names of things and where are things, right? So chordae tendineae, papillary muscles, that's more of a lab thing that you're going to have to know. For lecture, I just want you to know what it does. And let me show you something else. Not that. That's like way. Hold on. Oh, that's showing you what we just talked about. That is what we just did with me drawing arrows and stuff. That's like a shorter way of doing it. And they're starting in the same place. Right atrium, tricuspid, right ventricle, pulmonary. Right? So you should know that. I want you to know that. I think that's what we talked about last class. I wanted you to know, and it doesn't really matter where you start, but you have two types of circulation here. You've got systemic circulation and pulmonary circulation. I'm going to mark the pulmonary circulation. So pulmonary circulation is when the blood leaves the heart, goes to the lungs, and back to the heart. So we will start around here. We'll start here. Pulmonary valve. Leaves the heart, goes to the lungs, comes back to the heart again. So I guess this top part. The blood's, yeah, you see how it's like, so the blood's leaving the heart as deoxygenated blood. It goes to the lungs, and then it returns to the heart again as oxygenated blood. That's the pulmonary circulation. Down here, we have systemic circulation. Leaves the heart, oxygenated, goes to all the places in your body, all your cells. That's what whatever this thing is represents, all the tissues, cells of your body. Leaves oxygenated, comes back through your veins deoxygenated, and goes back to the heart again. So this is systemic circulation. I'll mark it. You've got pulmonary circulation, you've got systemic circulation. There's actually a third type of circulation we're going to talk about in a second here called coronary circulation. So there's three types of circulation. One is when the blood goes from the heart to the lungs and back. The other circulation is when the blood goes from the heart to everywhere, all your organs and back. The third type is the heart feeding itself. The heart has to give the myocardium blood. And that is partly this. The heart has to feed itself a supply of blood. The heart itself is a muscle. It doesn't just siphon oxygen from the inside. It doesn't just take it from like a ventricle or an aorta. An atrium. You got to like go through the process too. So here's the blood leaving the heart. It's coming. It's once it's in here, this aorta, it's going to go to everywhere in the body, right? But look, like right here. Right here, you can see this one a little bit better. There's two of your coronary arteries. So this is coronary circulation. This is the heart giving blood to the heart, and the blood returns to the heart, which sounds kind of weird, but let's look at the arteries first. These are all coronary arteries. That's the heart feeding the myocardium. All these arteries are sticking into the myocardium, the muscle, and feeding it with oxygen. And it's all coming from here. See these two left and right coronary arteries. This is where people get heart attacks. You're not going to plug this up. I mean, you're messed up if you plug this thing up. Those are big vessels. I mean, things happen to them. I'm not saying that, but more likely you're going to plug up a little vessel, right? Those are easier to get plaque in, and it's going to be one of these. These up, if you got it up here, that's horrible. You're probably not going to make it through that. It all depends. If you got it, like, let's say right here, on this little vessel here, probably be okay. It all depends. Getting it, if you starve the blood supply to the left ventricle, that left ventricle is sending blood out to your entire body. That's serious. If you're starving the blood supply to somewhere, let's say in the right atrium, or the left atrium even, well, blood's mostly just kind of filling in. And if you remember, blood just kind of drops from the atrium into the ventricles. There is some pumping. The atria do contract and push some blood into the ventricles, but most of that blood, remember like that trap door and the blood like starts building up and it opens up and it opens the trap door. So if you have to choose, if you had your choice, you're getting a heart attack, where do you want it? I would always go with atrium because not that the heart's going to be perfect, but like it could still kind of work, right? I don't want the ventricles. And if I have to choose a ventricle, I don't want the left ventricle. The left ventricle is pumping blood all the way to my feet and back. The right ventricle is pumping blood just next door to the lungs. But it all depends on what gets plugged up. I mean, that's essentially what a heart attack is. One of these vessels are getting plugged and you're starving. Like let's say that right here, we're gonna put our our plaque right here, right? That means that this area right here is not getting any oxygen. So this area here, I've killed it. I've starved it of oxygen, and those cells aren't gonna, if it gets bad enough, they're not gonna work anymore. Like it doesn't come back. I've killed that muscle. So can I run the heart with the rest of this? Am I okay? Can I still live? Can I run it? It all depends. If you block here, that'd be like, they call that a widowmaker. Like you block that, and you block all of this. So not good. But anyway, this is feeding the heart. So let's look at the return trip, all the veins. These are coronary arteries. Let's look at the coronary veins. Yeah, but it won't just oh, we got it set up. Oh.
It still says freeze too at the top.
Boy, does it?
Yeah, on the right hand side. Oh, when was it should work
There. I don't even know if I can.
So what happens to people that have like they're born with it? Do they have all of these? Like,
Half hearts?
yeah, I don't know if I'm saying that right. But like, you know how when some babies are born and they have like a little bit of a heart. I don't know.
They're going to need the whole thing. They're not really going to be able to live. Sometimes they're born with things not closing completely, like there's holes in between the atria or there's holes in between the ventricles, like that. I know that happens. You just gotta, like, they'll have to go in there and seal it up. This is the return. Right, so this is all the blood, the deoxygenated blood coming back through the veins, and all of these veins you see, the ones behind the heart, because you got to remember there's ones on the other, if you flip it around, there's coronary veins on the other side. They're all going to empty into this coronary sinus, and the coronary sinus is right here. So I'm going to outline, it's kind of hard, but I'm going to outline the atrium. I'm going to take my best shot at it. That's an atrium. Like this whole thing is the right atrium. There is that circle that I'm making here. There's the opening for the coronary sinus. So you can't really see it. It's inside the heart. It's inside the right atrium. But that's the blood. All these coronary vessels all go back in. So let me just see if I can show you if they got a picture of like the regular heart. Let's see again. All right. Anyway, that's all going back in. I don't know. There's a picture of a heart, like an actual heart. It's kind of hard to see. kind of hard to make out where things are. I think we're looking like a little bit from top down. And then, we're looking at the front, but it's kind of at a diagonal angle. Like you could see, this is like the coronary, it's one of the coronary vessels, but that's not really what I wanted to show you. So here's the blood leaving. This is like a ventricle, whatever. I'm not drawing it well, but this is the, and then this is the valve here. That's like a valve, and then that's going to go into the aorta, and you know the aorta arches, right? It arches and it just drops all the way down behind the heart. So there's a ventricle. Here's the atrium. So, and then there's a valve, right? So blood's in the atrium, gets put into the ventricle. Now the blood's in the ventricle, and it's got two doors. There's two ways out. Well, this isn't a way out, right? So this AV valve is going to shut closed, and the blood's going to go this way. There's the blood. So here's the blood. The ventricle contracts, and now the blood's been pushed out of the heart. Here's the blood. It's just been pushed out, right? As soon as this ventricle relaxes, this blood is going to try to drop back in because there's no pressure. You're not forcing it. You squeeze it and force it out. Soon as you like relax it, it tries to go back in, and it's going to shut those two. That's a aortic valve. It's going to shut the aortic valve. And instead, what's happening is that there's one of the coronary arteries. So it tries to go back in. It can't. Some of that blood is going to go into here, and that's going to feed the heart. Same thing, there's one like on the other side. So every time your heart relaxes, that blood tries to go back in. It shuts the valve, and some of that blood goes into here and into there. That's feeding your heart. And then the next heartbeat, it contracts again, and here's like the next part of blood, right? This thing's going to contract. It's going to open up. This blood's going to go here. This blood is going to push up, and it's going to be here. And then it's going to relax again. Some of this blood's going to come back down and go that way and go that way. Because it can't get back into here. So that's more of like physiology. Like I'll probably, maybe, I'm hoping I've got like a picture of it somewhere, or I can get a video together of it or something. But the whole thing about coronary circulation is just kind of driven by when the ventricle's relaxing, or when the whole heart's relaxing, actually. So let me get this back on. Gotta make sure we stop to take a break, which is going to be like in the next 5 minutes, maybe 5-6 minutes. But let's talk about, the heart. The heart looks like, if you were to take the heart and like chop it up and make fajita out of it, there's a good chance you wouldn't be able to tell. It's like, it looks like steak. So if I were to put that into a burrito, you probably wouldn't know the difference, right? So it kind of looks like skeletal muscle. It looks like heart meat, like the myocardium. It looks like just any other skeletal muscle. But there's big differences between how these two muscles work. And the big difference with heart muscle is that it's all got to go at one time. The whole atrium have to contract at once. So that electrical signal, we call that electrical signal like the action potential, it has to move through the entire atria at once, and that whole atria has to contract. You can't have one side kind of contract. Maybe the left side will go full strength, but the right side will go part. No, it can't go like that. Both atria, all of the cells, all of the muscle cells, muscle fibers, they've all got to contract at once. Then it's the ventricle's turn. The whole ventricle has to contract at once, like both sides. And the whole thing, you can't have the top part of the ventricle contract, whereas the bottom's not really contracting. Everyone's got to fully commit. All the cells have to commit at the same time. Your skeletal muscle's not like that. You could have some fibers contract, but other fibers not really contract. Think about if you're lifting things that are really heavy versus light things. You're not using all your muscles to lift up. Like I'm lifting this eraser, right? My bicep's not going at 100%. I'm not using all my bicep fibers. Even someone like me, I'm not using all of them to lift this thing, right? But if this was like a gold brick, then I'd end class and leave. And also it would be a lot heavier and I'd have to use a lot of my, a lot more of my, my bicep muscle fibers, right? So your skeletal muscle, you can kind of play. You can go part way, part-time, full, but not your heart. It's all got to go at once. So it's while the fibers look like skeletal muscle, they've got some differences, right? And so here, let's see. I don't know how they have this. Like here's one heart cell. Like here's one myocardial cell. Here's another one. I don't know, they're branched, but you get the idea. So here, in between one and the other, I need that electrical signal to go from here to here without any delay. It has to be like simultaneous, like a split second, right? So they have these things in between them called intercalated discs. It's already written up here. I'm just gonna write it a little bit bigger. There are these intercalated discs, and they have these like holes in them called desmosomes. Anyway, it's set up so that there's nothing to stop it. You don't have to go through like a plasma membrane, or in the case of the cell, a muscle, we call it like a sarcolemma. You don't have to go through that membrane. It's just like there's holes in between. In between these two cells, there's like holes, and that electrical impulse can just go like immediately. Right, so it acts a little bit different. It's for one, heart muscle is autoarrhythmic, meaning that it excites itself, much like a dog. It's autoarrhythmic. It generates its own action potential, its own electrical impulse, right? Our muscles don't do that, right? Our brain has to generate it, and it has to go down through neurons and make its way to wherever it's going to go. But the heart makes its own, it's got its own pacemaker. And then the other thing is that, it works in unison. The atrium contract, then the ventricles contract, then the whole heart relaxes, and then we start over. Okay, we're going to take a break here. This is kind of a good place to stop. When we get back from break, I'm going to start on physiology. So far, I've only talked about one thing that I'm really going to test, that I might test you on for your quiz. And we're not going to get to the whole heart for the quiz. I'm not looking to do that. We're just going to, whatever we get through after break, that's what we're going to get through. But right now we have one question, and it's a difficult question because it's talking about where blood goes in the heart. Like, start with the right atrium. Where does the blood go next? where does it go next? Where does it go next? Right atrium, this is where we left off at the end of last class. Right atrium, tricuspid, right ventricle, whatever's after that, pulmonary valve, pulmonary trunk, pulmonary arteries, pulmonary veins, like that. And remember, I'm saying it like, then the pulmonary veins, then back into the left side. But remember, the blood's leaving both sides of the heart at the same time. I'm only describing one side at a time. I'm talking about what happens on the right side, and we're talking about what happens on the left side. But really, for the heart, it's both sides are pumping blood out to two different places. But that was the only question from the end of the lecture. And it actually, I'm going to leave this one slide up because it could be, it's this slide that we have. It is. It doesn't want to unpause now. Well, anyway, the slide that I'm going to pull up is where what I want you to know for. Whatever, I'll pull it up on here. That one. This is what we did. This is where we ended last class. So let's take a break. That's the only thing I really want you to know as of this point that I would test you on. And then in about 10 minutes, we'll start talking about the physiology, because right up to this point, we've been talking about the anatomy of the heart. Now I want to talk about how it works. How do the muscle cells contract, things like that. So I'll see. Does anyone have any questions before break?
What figure is this in the book? Figure 20 what?
That's not going to be in your book.
Oh, okay.
Yeah, I mean, it is, but it doesn't look exactly like this.
Gotcha.
It's actually in your book. I imagine it's 19 something.
Okay.
But yeah, there is one like this, but it doesn't look exactly like that. All right. Otherwise, I'll see you guys in like 10 minutes. You good? I'm back. You need to know this. So let's start getting into the physiology, heart physiology. So here's your heart. This is called the cardiac conduction system. So an action potential, or like that electrical impulse, it has a place where it starts and it has a place where it ends. Right? And it's listed right here, actually. So the pacemaker of the heart is in the right atrium. It's up here, the sinoatrial node, the SA node. So that's the pacemaker of the heart. You could see like these arrows where it goes, right? So that action potential is immediately going to the complete aorta. I keep calling it aorta. It's going to this right atrium, like the whole atrium, and it's coming over to the left atrium. So the SA node is going to make both of the atria contract. Of course, a little bit of this next one too. So you have another node here called the AV node, atrioventricular node. That's kind of, it's hard to see here, but it's kind of at the AV node is kind of the junction of where the two atrium and the two ventricles are. Sometimes if the SA node fails, the AV node could start to pick up and start acting as the pacemaker. You're not going to be running any marathons or anything, but it could do that, But usually when someone gets a pacemaker, we're talking about like a new SA node. Then what happens is that right here, we call this thing a bundle branch, right? So this is we're now like at this space where the two atria and the two ventricles are kind of all joined together. This is the beginning of the septum. So we call this the bundle of His, or you can call it the AV bundle. And you see it's going to branch. There's going to be a left branch and a right branch. So that's kind of one thing that sometimes happens with hearts is that you get a lot. They call it like a bundle branch block, right? So in here, like the signal doesn't go through here; it gets impeded somehow. Or maybe another thing that'll happen is that maybe some of these start to turn into like SA nodes. So maybe you've got too much firing inside here. So like it's supposed to be like a coordinated, the action potential goes here, then down here. It splits, and then it goes like this around the apex of each ventricle. It's just supposed to keep going like that. Sometimes things happen. You get down here, and then like shoots off a few of them. Right? You don't want that. You have to go in there and like cauterize it, find them and cauterize them. But often what happens is it gets blocked. But anyway, the left and right bundle branches. And then here we call these the Purkinje fibers. So it comes around the apex of the heart and it's going around both ventricles. So this thing happens so quick that the whole ventricle contracts at once. It's not a slow process. It's not even a blink of an eye between the time it's here and it's here. It does this so fast that it's like it happens at one time, right? This whole ventricle is going to just contract. And when it goes from here to here, from like 1 to 2, it happens so fast that the atria contract, right? So the atrium are contracting first, the ventricles are contracting second. And then when it gets to here, it dissipates, the whole heart relaxes, right? I keep saying these 3 steps. Atrium contract, ventricles contract, whole heart relaxes. So this is kind of easy in that you just have to memorize the order. If I ask you on a test, you pretty much regurgitate this. I mean, that's really all there is to it. But you know, if the SA node, just keep in your head, if the SA node fails, the sinoatrial node, you're going to call it sinoatrial. If the sinoatrial node fails, then the atrioventricular node can take over. I mean, they even say that the atrioventricular bundle could take over. But so when you see, like, you know, when they take the paddles, people think that like sometimes that those paddles, I'm just thinking of something, you know, we should bring some of those in for lab. And I've got some trainer kits we could like at least train to use the AED. So when they're using those, it doesn't bring someone back from like no heartbeat. It doesn't work. It only works on two things. It works on something called VFib, ventricular fibrillation. I can never say that word. And then VTAC, ventricular tachycardia, when the heart. So sometimes what will happen is that the ventricles down here, like somewhere down here, these will act as pacemakers. You'll get like a bunch of pacemakers down here. And so they're all starting to be the leader and be like the SA node. And so you get this quivering, right? Because you're only supposed to have one pacemaker, you know, one leader of the band. You've got a bunch of people trying to conduct, right? So then you got to reset. So you just shock this thing and hopefully it'll reset and start back here again. Or you get some pacemakers in here where they don't belong in the septum, and they start just firing. And now you just got a bunch of firing, right? And the ventricles are just, and there's the danger with that is, I mean, you might think that like, okay, we're gonna contract, and it's gonna push out a bunch of blood. No, because you squeeze out blood, you got to let it relax, and you got to give it time to fill up again before you squeeze again. But if you squeeze and squeeze and squeeze, it's not going to refill with blood. So it's actually, you're not getting blood moving around your body. You're just making this thing, you're in VTAC, right? So if you're in VTAC or VFib, that's what you use the paddles for. You just reset the whole heart. It doesn't work for dead people. It's not used nearly as often as people think they are. All right, but memorize this. And then I want to talk about how the cells themselves contract. This is the order that they contract. You know, when the action potential is going through here, these cells are contracting. When it goes through here, these cells are contracting. You know, but what exactly is going on when a cell contracts? When a muscle cell contracts? You know what? I don't even need this thing on. All right. This is very similar to the muscle physiology you had in AMP1, but the heart's a muscle too, so you know, we got like. So I'm just going to draw. That's a heart. I'm going to draw a little bit longer. That's a muscle. Well, I'll draw another one now here. Okay, that's a muscle cell. Muscle cells are called muscle fibers. So if I call it a muscle fiber or muscle cell, it's the same thing. Muscle cells are not like round. We think of cells as being like round, right? No, they're long. They're really long things that can, you know, this is contracted and then this is relaxed. So there's all these proteins built in, and you already had that, so we're not going to discuss it. But you know, the actin and myosin and stuff, they're all built in here to make this thing contract and get smaller and then go back. So how does it happen? What's the electrical thing that makes it happen? Well, there's three primary electrolytes. Remember, electrolytes are minerals. Salt is an electrolyte. Salt is made from sodium and chlorine. Those are both electrolytes. So electrolytes are minerals that are like minerals that we use all the time, and they have charges. If you don't know already, you have to start learning these minerals and what charges they have. So if I say something like sodium, which is Na, you automatically should think that sodium is a cation. They're always positive in your body, right? And then there's certain things like chlorine would be negative, iodine negative, things like that. So there's some that are really important ones, like phosphorus. Phosphorus is negative, calcium's positive. Potassium is another positive one. And not only that, not only should you know if they're positive or if they're negative, you should know where they tend to hang out. And there's one of two places. Either these minerals hang out inside of your cells, or they like to hang out outside of your cells. So we call that intracellular fluid, and extracellular fluid. So electrolytes prefer, like sodium is extracellular. It likes to be outside of your cells. Potassium is intracellular. It likes to be inside of your cells. It doesn't mean that they won't be outside of your cells. You could find potassium outside of your cells, but this is where they like to hang out. You tend to find them inside of your cells. So here we have sodium and potassium. Sodium is extracellular, potassium's intracellular. They work together. It's like a marriage. They work well together raising the kids, but they don't want to be in the same room at the same time. One comes home, the other one's like, oh, I got that thing I got to go to later. And that's the magic of their relationship. They get along so well because they don't hang out together in the same room. So that's kind of, so right now, let's look at this. Sodium's hanging out outside, potassium's inside. Don't look at it right now as sodium and potassium. Look at it as positively charged things, right? Ions. So if we're looking at positively charged, they're equal. There's an equal number of positively charged on the inside. There's an equal number of positively charged on the outside, right? So I just put 3. There's 3 positive sodiums on the outside, and there's 3 positive potassiums on the inside. I just used 3 just to. So what's going to happen right now, we can call this polarized. What we're going to do is we're going to throw it off balance. We're going to depolarize it. And what happens is that there's all these doors that are just for sodium, and they're going to open up, and sodium's going to rush into the cell. So I put them all in the cell, and that's it. This is depolarized. That's the key word. The whole feng shui of the cell is all fucked up now. They're all inside. That's going to cause this cell to contract. So depolarization causes contraction. So it's thrown off now. There's no positives outside. They're all inside. They're all together. Of course, they don't like to be like that, right? Remember, sodium and potassium, they work well together. They don't like to hang out. So some of the potassium's like, yeah, I got that thing at the place, and they start to make their way for the door. So some of the potassiums are starting to leave. And I'm just going to have one of them leave here, but some of them are going to start to leave. And what happens is that if all the potassiums leave, it's going to go back to how it was before, right? We need to keep it contracted. We don't want it to relax yet. And some of the potassiums are leaving because they secretly don't like sodium. They're annoying. Sodium walked in. Oh, hello, what's going on? And potassium's starting to go, but we don't want the contraction to end yet. So luckily we have calcium. Calcium is by and calcium's going to start to trickle in. So when one potassium leaves out the front door, calcium's going to come in through the back door. That's like the neighbor. Right? Hey, I saw you pull up in the driveway. What's going on? So calcium's starting to come in, but calcium's only a neighbor. Calcium's not living there. So calcium's going to say hi. Sodium's going to be like, yeah, I'm fine. Just like yesterday. Go leave, and then calcium will eventually turn around and start to leave. But calcium does flow in for a little bit. Calcium holds in to hold that contraction. We call this a plateau. So there's depolarization. Kind of happens in 3 stages. That's going to make the muscle contract. Then there's a plateau. Plateau period is when calcium's starting to trickle in, just to kind of hold that contraction for a brief fraction of a second, right? And then finally, the calcium turns around and goes back home, and the potassium keeps coming out. So now we've actually switched places. Sodium came in, the potassium left. We call that repolarized. It repolarized itself. It's going to relax. Started to write L for relax. Then the cell will relax again. When the potassium leaves the cell relaxes. So sodium rushes in. That's going to make the cell, that's going to cause the cell to contract. Calcium trickles in to kind of hold that contraction. Potassium leaves. And it relaxes again. Now you're at this place. Here's the part that is kind of inefficient sounding. It doesn't sound very intuitive. While the cell's relaxed, they're going to swap places. The sodium and the potassium are going to trade places again before we have another heartbeat. So it's not like potassium's going to rush in and make this thing contract again. Because that kind of makes sense, right? Well, why doesn't the potassium go back in and we'll run through this again, do another contraction? No, they trade places. They've got like these doors. As one goes in, the other is forced to come out. So they swap places again before the next heartbeat. Which I did wrong. So we're back with the potassium on the inside again. It resets itself before the next heartbeat. Here's all the sodiums on the outside. Then they swapped places before the next heartbeat, and then it starts all over again. Sodium turns right back around, goes back inside again. Potassium starts to leave a little bit. Calcium comes in. Then all the potassium leaves. Then they swap places again. They start it again. So we've got 3. I've got the slide that when I turn the projector back on. We've got 3 stages to this. The depolarization, sodium rushes in. The plateau stage, calcium trickles in. Hold that contraction. Repolarization, the potassium all leaves. It's repolarized. I've got this whole process in another video. Hold on, it's turning on. I'm trying to figure out how to get rid of this thing. There we go. All right. This is the same. This is what I was talking about. We're not going to deal with membrane potential in millivolts. If you take an EKG class, you will, but we're not going to deal with it. It's just showing you step one. It says rapid depolarization due to blah, 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 whatever. It's saying that there are these channels. Channels are like, they're gates, they're openings in your cell. So if you look at a cell membrane, I always imagine a cell membrane as like a wall, right? I imagine a cell membrane as like this wall, right? So I got sheetrock here, and then when you come out on the other side, I've got sheetrock here. So I got 2 layers of sheetrock, right? And then inside here in the middle, there's either wood, like your house, it's wood, or it's metal, right? That's what our cell membranes are like. It's got 2 phospholipid bilayers. That's the sheetrock. And then inside, you find a bunch of like proteins and stuff. But also you got other things like back there, you've got windows. And then of course you got like this door. And there's something like this thing. Those are all proteins. Like this would be like a type of receptor. This door would be like a channel to let things in. Some doors are big and some doors are really small. You can make like a huge garage door in this wall, and that would be like a sodium channel. All of a sudden you've opened this huge door and the sodium's just going to flood into the cell. And you can also close it. So things that are ions, they use their own door. Potassium has its own door. Sodium has its own door. Calcium has its own door. Everything has its own door in the cell. So that's what they're saying, that those doors that are just for sodium, they open up and the sodium rushes in. Then the door, and that's going to cause depolarization. And it's going to cause the muscle to contract. Then calcium, and I wasn't writing Ca2, but I mean, it doesn't matter. It's calcium. Calcium trickles in, and that's going to let and you see they're called voltage-gated slow calcium channels, meaning that calcium's trickling in. It's not rushing in like sodium did. So that's the whole discontraction. That's the plateau phase. Then you have repolarization. Those doors, potassium had been kind of trying to trickle out, but now the potassium doors opened up and potassium could just rush out. And that's repolarization. You're going to have relaxation of the cell. So again, don't get hung up on the membrane potential, but just imagine the cell, and you have these 3 electrolytes, sodium, potassium, calcium. They're working together to make that heart muscle contract and relax. And that happens with every heartbeat. Every time you heartbeat, all the sodium rush in. The calcium trickles in. The potassium rushes out. And then the sodium and potassium swap places, and they start the whole process over again. 60, 70 times a minute, day after day. So really important words here, are depolarization and repolarization, right? Because depolarization, you're going to associate that word with contraction. Doesn't guarantee that you're going to have a contraction. It's because we're really talking about the electrical impulse. Depolarization means that the electrical thing happened in my muscle cell that's going to make it contract. Repolarization, you associate that with relaxation. They both start with R. Let's look at this more practically. So there is an EKG. An EKG is looking just at that. It's looking at depolarization and repolarization. And if you look at it, there's 3 parts. On with the electrical signal in different parts of the heart. I am not good at doing these. There's a few things that I know. I know this one. I'm good with that. That's called asystole. I'm good with this one. That means like tachycardia. Other things, I don't know. There's a class you can take here that Katie teaches just on EKGs. I can. The first thing here is a P wave. And then where it goes up and down and like that, we call this a QRS complex. And then the T wave. So PQRST. Hope you don't get that wrong because it's in alphabetical order. P wave.
Is everyone messing up?
Yeah, I had to open up a new one.
Oh, okay.
Yeah, his started. His screen was paused.
Mm-hmm. I still don't see him.
I don't see him neither. Yeah.
I know, me either.
I wonder if he noticed that his computer done shut down.
I'm gonna send him a message.
Should be on because it's still recording.
That was me. I'm hotspotting now. I don't know. Something happened with the connection at Nunez. So, can you guys hear me? Somebody just unmute themselves.
Yes.
All right, okay. I don't know what that was. That's why I'm on pretty low battery anyway. So what do I got? I've got 12% battery. All right. So if we do shut down, before I can go over quiz questions, I'll make a separate video like right away with the quiz questions and stuff, and I'll post it separately. So, all right. So, P-Wave. What did these? Oh, this is on a different slide. That's right. All right. So let me just go to the slide. I've got it all done how you need it. Not that. That. All right. So P-wave atrial depolarization. That means that the atrium are going to contract. QRS complex. That was the next one. That means the ventricles are going to contract. Right? And then finally, the T wave is going to tell you that the ventricles are going to repolarize. In other words, relax. That also means, by the way, the T wave, it also means that the atrium are still relaxed. The atrium are still relaxed. So atrium contract, ventricles contract, but you know, when the ventricles contract, that means that the atrium are automatically relaxed. They don't all contract at the same time. They can't. So if the ventricles, so for example, the atrium are contracted. That means the ventricles have to be relaxed. Here, atrium are contracted. That means the ventricles are relaxed. Ventricles contract. That means the atrium are relaxed. Now here the ventricles relaxed. The whole heart relaxes. It's like the 3 stages. Atrium contract, ventricles then contract, then the whole heart relaxes. But we're not saying that. We're talking about the electrical signals. So that's why we're using these words depolarization and repolarization. This doesn't, like technically speaking, it doesn't mechanically mean that, yeah, see, I'm running low on battery already. Wow, that was quick. Hold on, let me see if I can charge it over here. If it doesn't reach, I might go to, it's not going to reach. I'm going to have to go to, yeah, or I can go in here and do it. But I can't share my screen. All right. I hope you got most of that EKG stuff. I think I was going to try to end it there anyway, which works out really well for you guys because I don't even know if I got 5 questions. I mean, I think you know literally all the questions that are going to be on the test. So I'm going to use the chat box here. So let's talk about these. And we're going to end a few minutes early today too. All right. So first thing you needed to know was and I don't know how I'm going to ask it, but it's like the path of blood flow through the heart. I don't care where you start, although most of you are going to start on the right atrium. But I want you to, and I want you to know which of those, for the path of the blood flow, I want you to know which is systemic and versus pulmonary circulation. You know, and really, it's not that difficult. Pulmonary circulation starts, just, you know, answer that question. Pulmonary circulation is when the blood, wherever that blood's leaving the heart to go to the lungs, and when it comes back. So you pretty much start at, let's say, the right ventricle, I guess. So after the right ventricle, it's going to go through the aortic valve, and it's going to go to the, not the aortic valve, the pulmonary valve, and it's going to go to the pulmonary trunk, pulmonary arteries, come back to the pulmonary veins. That's it. So once you write everything out, like write it all out first, write everything out first, and then go find probably like the, let's say, pulmonary valve. All the pulmonary words, pulmonary valve, pulmonary trunk, pulmonary arteries, pulmonary veins, that's your pulmonary circulation. All the pulmonary words. Everything else, by process of elimination, is systemic circulation. So you don't actually have to memorize systemic circulation, just start with pulmonary. And then whatever's left is going to be systemic. So that'll be like a listing question, right? You know, this, then this, then this. I mean, there's no way for you to write a story about that, is there? Question number 2. The cardiac conduction system. That was the one with, and again, an easy question. You're listing sinoatrial node, atrioventricular node, atrioventricular bundle, the left and the right bundle branches, Purkinje fibers, number 5. You got to learn how to spell the words, but you're just listing which one is the pacemaker, the SA node. Which one, what if the pacemaker fails? Can anything compensate for it? The AV node. You got any question, Brittany?
Huh?
Do you have any questions?
No. I pressed something?
Yeah. No, I think you turned your mic on. It's okay.
Oh,
There's
no.
no law against that. Third one. How, I spelt it wrong, but how are action potentials formed? That's like something that you're going to explain. If you need to draw a picture to help you with it, you can, but you don't have to. But it's the whole part about the sodium rushing into the cell with the potassium that's already there, and that's going to cause depolarization. Use the words depolarization. I want the words. Those words I want because they're used. You're going to start using them. So, sodium rushing into the muscle fiber causes depolarization. Then calcium is going to trickle in to kind of maintain that polarization. You know, the plateau phase. And then you write something about how the potassium will start, you know, quickly leaving the cell, and that's going to repolarize the cell. So, you know, just write that one out a little bit. You know, write it so that I know you understand what's going on. Just don't flip words. Like, don't just put.
So would you rather us like do the 3 different pictures like you had with the sodium and the potassium?
Yeah, you could.
Okay.
You know, like, okay, so you probably want it, like, you would want to know, like, what am I looking for to mark that question correct? I would mark that. Yeah.
Okay.
When I would look at that, I would say, yeah, she understands that. I'm only looking to see you understand it. If I can figure out that you understand it, then it's correct. Yeah.
Okay.
I mean, obviously, if you have the right answer is the right answer, no matter what. But maybe you aren't using like all the big words you're supposed to use. But if I see you're understanding what's going on, then I'm a little less judgy on that. But if you just write, for example, some people would just say sodium depolarization, They would just write Na depolarization. Then right underneath it, they would write Ca plateau. You know, how do I know that you know what that means? Those are just words. You learn how to put one word underneath another word. Like, you have no idea what's going on. You just wrote words because you crammed. I'm not talking about any of you. I'm just saying, right? So if you drew a picture explaining what's happening, that's, or if you don't like to draw pictures, you just write it out. If I know that you could tell me what I told you in some form, then I'm good. That's all I want. So we're on question 4 now, and this is probably the last question because I don't think I'm gonna have to struggle to come up with a 5th question. All right, but let's do the 4th one. Explain the parts of an EKG. Here's question 4. Explain the parts of a EKG. So, and that was that last slide. That one I've got up on the board. I don't know if you can see it. And I've got a video on it. I've got like another video on it that I'm about to post right when we're done with class, which is about now. Don't just say, don't just say P wave. What's happening with the P wave? That's atrial depolarization. That means that all those electrical impulses are going through the atrium. In other words, if we were to match that up with like the SA node and the AV node and stuff, the P wave is the SA node and the AV node. The QRS complex is the like the other 3, like the bundle of His and the bundle branches Purkinje fibers. But anyway, I don't want to confuse you. But the P wave is atrial depolarization. The action potential is going through the atrium. The QRS complex is ventricular depolarization. So now the action potential is in the ventricles. The T wave is ventricular repolarization, meaning that the ventricles are relaxed. In fact, the whole heart is relaxed with the T wave. That's another thing we should do in lab. We should do some EKGs on someone. Probably on Kevin because it's just more appropriate to do it on a guy.
And then what if you come back in AFib? Then we have to call 911.
No, then we'll get those, whatever it comes back as, we're just going to get those paddles and shock it anyway, like on TV. Damn it, come back. Don't you fucking die on me. We're going to be like pounding Kevin's chest. Don't you fucking go, not today.
But I'm quite sure he's taking medication for AFib, so.
Oh, let's look at it.
That'll be fine. They already killing me at this job.
Oh.
Yeah, we'll tape it and send it to your manager. Like, look what you're doing to Kevin.
Well, that's why I had to miss last week's class. One of my associates didn't get up for the truck, and a guy called corporate, and we got in trouble. So I had to come and receive the truck.
See, never ends for him.
No, don't be a manager.
I think we're just going to stick with 4 questions. I mean, you guys need a win anyway. After your last exam that I curved 10 points because you guys sucked. You need something that you can just all get 100 points.
No, it wasn't that bad.
You didn't all get. Some of you did pretty well.
I felt like I did better.
Not if you gave 10 points.
I mean, even with 10, some of you got like 9. No one got 100, but some people got some 90. A couple of people got 95s, and anyway, look. This is going to be a win because you know what the 4 questions are. And 3 of them are kind of like things that you list. So you know exactly what 4 questions, right? It's not like I'm giving you 8 and I'm going to pick 5. These are the 4 questions. That's it. That's the test. You know what it is. You've got 2 days to like study it. So this is just do it. Just do it. Find the time, study it, do it. This is a win. This is 100. This is going to make your grade go up, and you're going to feel a lot better about things.
I do have one question before we end. For the when we explain the parts of the EKG, I know you were saying you know, when one contracts, the other one relax. You don't want that. You want it just the way it was on the slide, correct?
You can't go wrong with just the way it is on the slide. I'm not going to, like, what if you write extra and you were wrong? Or am I going to, like, mark you wrong? No.
Okay.
I ultimately, I want you to, like, be able to understand this all in your head. And you might, you know, that's not going to happen by Wednesday for most of you, and that's okay. So if you write stuff and you happen to be wrong, but I know that you understood the main part of the question, then I'm not going to, like, I don't. Some people are dicks like that. Like, yeah. You know, you get punished for trying to, like, think a little bit more and add more stuff. And it's like you're getting punished because if you put anything wrong, then you're going to get it wrong. Like, I won't do that to you. I would like you to know that, I'd like for you to picture in your head that it's like this hand is the atrium. So it's like contraction, contraction, relax, contraction, contraction, relax. But I don't know. There's some good videos. If you look on just YouTube and Khan Academy's got some really good videos on heart physiology. We might watch one after the quiz. I think that's what we'll do. Since you guys will be here, we'll watch a couple videos on YouTube. So, all right. Let me stop recording, but if you guys got questions, I can answer your questions.